minus 2y is less than 12. So the first order of business is to graph that boundary line, right? So we need a line that separates all of the solutions from all the non-solutions. And that boundary line exists where the two sides of the equation are equal. So we can find that boundary line by graphing an equation. So we're going to start by graphing the boundary line. Which is just the same exact statement, but with an equal sign instead of an inequality sign. And to graph this equation, you can use any of the graphing tools that we've talked about in the past week. So like, because this is in general form, I would probably just use the intercepts. So if I put 0 in for x, then that term goes away, divide both sides by -2, and I get that y is -6. So 0, -6 is my y-intercept. And then if I put 0 in for y, then this term goes away. And so I can divide both sides by 4, and I get x equals 3. So my x-intercept is 3, 0. So when it's in general form like this, I often will just like cover one of the terms up like with my finger and be like, okay, if I put a 0 there, that's gone. And then you're just dividing by a single number to get your intercept. And so it's fairly simple to come up with those intercepts rather than like solving the whole thing for y, which can open you up for error. So we have 3, 0 here, and then 0, -6 is right here. So here's my boundary line. And then we need to determine if we're including the points that are on that line or if we're not including the points on that line. So the points on that line are where the two sides of this inequality are equal. So if we have a strict inequality, we don't want to include those, because if I say that 4x minus 2y is less than 12, then 4x minus 2y being equal to 12 is not part of the solution set, right? This isn't an or equal to situation. And so decide on what type of line. So inclusive or strict inequality. We call an inequality inclusive if it's the or equal to variety, and we call it a strict inequality if it doesn't include the values where the two sides are equal. So if it's a strict inequality, then we use a dashed line to show that we're not including the points on the line in our solution set. And then if it's inclusive, we use a solid line. I'm not condoning using pen, but if you do use pen, you should probably make this decision before you actually draw the line. But if you use pencil, which I know you all do, then you can just go in and be like, okay, I'm going to make this into a dashed line. Does that make sense why we chose the dashed here? Okay. And then the last step is to determine which side to shade. And so like I said before, if you find one point that is a solution, you know that every single point on that side, the same side of the line, is a solution. If you find one point that's not a solution, you know every single point on that side of the line is not a solution. So we're just going to use a single test point. So we're going to say, we're going to choose a test point. I usually choose 0, 0 because zeros are easy to do calculations with. So we'll use the test point, and we just plug that in. So we're plugging this into the inequality, like the original one right here. So we change that to an equal sign just for the purposes of drawing that line in step 1. That's the only time we use an equal sign. Otherwise, we're using the inequality sign. So we have 4 times 0 minus 2 times 0 is less than 12, which gives us 0 is less than 12. Is that true?
Yes.
Yes, 0 is less than 12, which means that 0, 0 is a solution. So if it's a solution, we will shade the entire region, including that point. If it's not a solution, we will shade the entire region, not including the point. So you don't have to keep on picking points to find a solution. You just have to test one point. If it's not a solution, then you know everything on the other side is a solution. And so it's not a matter of like choosing points until you find one that works. We're just using the one test point. And in this case, our test point is right here at 0, 0. And we said that is a solution. And so everything to the top left of that line is going to be a solution. And so we're going to shade that entire region.
Does 0, 0 always work?
The only time you can't use 0, 0 is when it's on the line. So when you choose your test point, it has to be a point that's not on the boundary. But as long as 0, 0 is not on the boundary, then it'll work. I mean, really any point will work as long as it's not on the boundary line. I just use 0, 0 because it's fairly easy to work with. Let's make this bigger. Here we go. So shade, 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 shade. We'll do a few more examples, but does the basic idea of what we're doing here make sense? Good. Okay, let's do a few more. Let's graph y is greater than or equal to 4x minus 6. Okay, so first things first, we're going to graph an equation. So we're going to graph y equals 4x minus 6. This one is in slope-intercept form, and so we can just use the y-intercept 0, negative 6. 1, 2, 3, 4, 5, 6. And then our slope is 4, so that tells me that if I move to the right 1 unit, I'm going to go up 4 units. So right 1, 1, 2, 3, 4, up 4. That gives me another point. And there's my line. Whoa. So that's my boundary. And then we want to know if this is going to be solid or dashed. And I usually actually like write this down just to force myself to think about it every time. It's easy to like get in a hurry and kind of like skip over this step because you already drew the line. So would this one be solid or would it be dashed? It would be solid. And that's because it's the greater than or equal to type of inequality. One way that helps me remember is like if there's a straight line, like if there's a line in the inequality, then your line is going to be like a line. So we'll just leave it as is. And now we need a test point. What do you guys want to use?
0, 0.
Okay. You guys are so agreeable. I've had people be like, do 100, 3072. Just to be pains. Okay, so 0 is greater than or equal to 4 times 0 minus 6. So we get 0 is greater than or equal to negative 6. Is that a true statement? It is. So true. So there's my test point at 0, 0. I'm going to shade everything that includes it. So when you do this shading, if you find that point, if it's a true statement, your shading should cover up that point. If it's not a true statement, your shading should not cover up that point. So all this stuff. And one thing that is true, but you have to be a little bit careful with it, is if it's in slope-intercept form. So if y is by itself on one side of your inequality, it is true that like if it's a greater than, everything above the line is shaded, and if it's a less than, that everything below the line is shaded. It's a little bit difficult to see here that we shaded above the line because it's such a steep line that it looks more like a left or right situation. But the points, all the points that we shaded, notice, are like, if we made it a little less steep, it would be above the line, right? So it is true that if you're in slope-intercept form, you can think of it sort of that directly, that if it's greater than, it's above, and if it's less than, it's below. Okay, here's one for you guys to try. So graph negative 4x plus y is greater than or equal to 8. Or you can just use your intercept, so you don't have to put it in slope-intercept form. And then it avoids any. you the point -2, 0. Like these are two separate points rather than one single point.
Oh, that's interesting.
Right, and then this one is 0, 8 because you put 0 in for x. And then that way you get the 2 points so you can draw your line.
For this one, would you just pull it out?
Yep.
So when we boundary line is this one.
Yeah, this is the boundary line.
So you just shoot from here under.
Yep.
If it was true, you shoot.
Yep, exactly. Good.
Okay.
Okay, so this one's in standard form. So probably most convenient just to use intercepts. So if I want to graph -4x plus y equals 8, if you put 0 in for x, then this term just goes away. And so we end up with y equals 8. And then if we put 0 in for y, then this term goes away. And to solve for x, we would divide both sides by -4, which gives us, what, -2? -2, 0, and 0, 8. Oops. You also could have put it in slope-intercept form. I try to do as few manipulations as I have to, just so that I don't open myself up to make errors, like in moving things around. So I don't usually put it in slope-intercept form unless like the intercepts turn out to be like really nasty decimals or something like that. So then from here, I want to know if it's going to be a solid or a dashed line. What'd you guys decide?
Solid.
And then what test point did you use? 0, 0.
0, 0.
Everybody uses 0. It's good. Test point is 0, 0. And so we end up with -4 times 0 plus 0 is greater than or equal to 8, which is not a true statement. And so my test point is right here. I want to shade everything that's on the other side of the line. So the region that doesn't include that point is going to be all of this. There we go. So I'm glad we got one where we got to do the other side. Does that make sense? That's what I saw as I was walking around. Everybody seemed to get that. Any questions or anything look weird? Okay, let's do just a couple of special cases. So let's graph. We'll do y is greater than 5, and then I'm just going to do them both on the same. X is less than or equal to -2. So we're just graphing two separate inequalities, but I'm going to do them on the same plane because they're both pretty simple. What does the line y equals 5 look like?
It's a horizontal line.
Yeah, it's a horizontal line, right? The line containing all points with the same y value. means that every point on the line is the same height, and so it's really just a horizontal line that's 5 units up. And so we've got 1, 2, 3, 4, 5. And then it's going to be dashed in this case because that's a strict inequality. And then when we have horizontal and vertical lines, like you really don't have to use a test point. Like when I say y is greater than 5, I'm saying I want to shade all the points that have a y value that's bigger than 5. Where are those points going to be?
Above it.
Yeah, right? Because our y values go from smallest to biggest as we move up. So all the points above 5 are going to have y values that are greater than 5. So we don't have to use a test point here because there's no we don't have like a diagonal line where we have to like figure a whole lot out as far as the combination between x and y. We're just looking at one value, the y value. And so our solutions are going to be in this region here. And so then same thing for our other inequality. If I want to graph x is less than or equal to -2, we'll start with graphing x is equal to -2. What does that look like?
It's the vertical line.
Yep. It's a vertical line. So right here with an x value of -2. And this one is going to be solid because that inequality contains that or equals to line. And then again, because there's no y in this inequality, we don't have to worry about the combination of x and y. We're just looking for all of the values, or all the points that have an x value that is less than -2 or less than or equal to -2. Where are those points going to be?
Left.
Yes, to the left of that line. So that's going to be all of this. That makes sense. So those are sort of the ones that are kind of like the simplest ones, but it can be a little deceptive because if you try plugging in a test point, it can get confusing because you don't have anywhere to put one of your variables. But if you just think of it just straight up in terms of like y, if it's horizontal, then you're either going above or below the line, depending on if you're less than or greater than. And same with the x values, either left or right. Any questions on those ones? These make perfectly, wonderfully good sense. Yeah. Good. Okay. Let's do one example where we can't use 0, 0, just so that we practice one of them. So when you get to one, it doesn't trip you up. Let's graph y is greater than 1/2 x. So we'll start with graphing our boundary line. Typically when I have equations like this that don't have addition or subtraction in them, I just plug in a couple numbers. Like I can't find, there's only one intercept because this line goes through the origin, so it goes through 0, 0. So plugging 0 in for x gives me the same point as plugging 0 in for y. And so my intercepts won't give me two separate points. But you can just make a table, or you can be like, oh, well, if x is 2, y is just going to be 1, because that equation says y is half of x. So when you have a simple equation like this without any addition or subtraction, probably the simplest way to graph it is to just pick a couple numbers and throw them into the equation to get a couple points. So I have 0, 0, and then 2, 1. And then do I want a solid line or a dashed line here?
Dash line.
Mm-hmm. And then we'll pick a test point. We cannot pick 0, 0 because 0, 0 is on the boundary line, right? So in order to make a decision about points on either side of the line, we have to pick a test point that is on one side or the other. If we're on the line, it's just going to tell us that the two sides are equal.
So we can just pick another easy thing like 1, 1.
Yep. That's usually what I use is, if I can't use 0, 0, I usually use 1, 1. Unless that happens to be on the line also, in which case you have to pick something else. But, so we have 1 is greater than or equal to 1/2 times 1, which gives me 1 is greater than, I'm sorry, I said or equal to, I didn't mean that, is greater than 1/2. And that is a true statement. So I'm going to find my point, which is right here. And I'm going to shade everything in the region that includes that point. So it's going to be everything up here. And again, notice that y is by itself on one side of the equation, and we have y is greater than, and so we shaded everything above.
So is it just a coincidence that every single example you showed, we shaded the top, or have you just been like choosing it like that?
No, it's a total coincidence.
Okay.
Yes, total coincidence. So here, you guys try this one. Oh, this is a good one. Y is less than or equal to negative x. Remember, when you have equations that don't have addition or subtraction in them, probably the simplest thing to do is just pick a couple numbers for x and find the corresponding y values. Because this equation, if you write y equals negative x, all it's saying is that the x and y coordinates are opposites of each other. So you just need 2 points where the two values are opposites. Right, so that gives you 0, 0. Right, if x is 0.
So that means I'd have to choose something else.
Right, yeah.
Okay.
0, 0,
Okay, so like I said, when we're graphing y equals negative x, like, so all that's saying is that the y coordinate is the opposite of the x coordinate. So if you pick like any number for x, the y coordinate is just the opposite of that. So you can pick pretty much anything. Sometimes it's easier to think of it in those terms than to try to like get really mathematical and calculate things. Because some of these like are deceptively simple, right? They end up just tripping us up. So 1, -1 is right here. 2, -2 is right here. And that gives us this line. And then is my line going to be solid or dashed? Solid, good. And then we can pick a test point. What did you guys use? 0, 0? So 0, 0 is right here, right? Which is on the line. So we can't use that. What else could we use?
1, 1.
Sure, 1, 1 would work. So we have 1 is less than or equal to -1. And that is false. So 1, 1 is right here, which means I want to shade the entire region that doesn't include that point. So that's all of this. And again, we have y alone on one side of the equation, and we have y is less than, and so that also shows us we want below that line.
I have a question.
Yes.
So if it's equal or equivalent to, why would you include a point that's on the line?
So we are including a point on the, so we're including the entire line. That's why it's solid, not dashed. We just can't use a point that's on the line to determine if the solutions are on the, if the rest of the solutions are on the left or right side or bottom or, right? Like if I pick, so if I were to pick 0, 0, I would go 0 is less than or equal to -0. Well, that's true, right? That's this point right here. But knowing that that point satisfies this inequality, does that tell me anything about all the points above it or all the points below it? Like how, I can't shade the region that that point is in because it's not in one of the regions. Right? If you're on the fence, then you don't know anything about what's on either side.
So maybe this is really wrong, but if it's less than or equal to,
Uh-huh.
you would just go below the line and shade everything in?
So that is true if y is by itself on one side. So we have y is less than or equal to -x. So yes, we shade everything below the line. Here we had y is greater than, and so we shaded everything above. But if you have this guy, for instance, y is not by itself. So we can't really make a conclusion about if it's above or below based on just the inequality. Because it depends on what lies on either side of it.
Okay.
Okay, so